Good morning, dear students. Today we're having the 12th practical lesson. It is about line integrals of the second kind. Actually, it is the last practical lesson of this module. And let me write down the general form of the line integral of the second kind. Let me remind you. So it is the general form. So we don't write down brackets here usually, so it's traditional form. And now let's start solving integrals. Let's start calculating integrals, and you will understand how to do it. So we will return to these formulas later when we have related tasks. Moment. We have the following integral. So, y plus x square dx plus 2x minus y dy. And we have the following not straight line, parabola. So 2x minus x square. And from point A11 to point B 3 minus 3. So A. So the following points. Okay, let we look at the plot, at the graph, so we can see it here. So point A, point B, and we will transform this line integral into the definite integral. So limits of integration by x from 1 to 3. So the following limits of integration. And what about y and dy? We will substitute this function. So dy equals 2 minus 2x dx. So we will substitute everything into this integral. So firstly, writing down limits of integration. So what do we have? So 2x minus x square plus x square, then plus 2x minus 2x plus x square, and multiplied by 2 minus 2x dx. Now let's simplify it a little bit as much as possible. So we can eliminate x squared here, and 2x will be eliminated here. So we have the following integral. Now let's expand the brackets. So 2x plus 2x square minus 2x cube. Okay, let me also move 2 out of the integral sign. And now we will integrate, finally.
Sorry, but why you remove the bracket after x squared at the start of third line?
Here.
Third line. A bit lower. Yes, here.
So plus 2x eliminated. So just only x.
Yeah, sorry. I see.
Main.
Thank you.
Never mind. So the antiderivative is the following: 1 over 2x squared plus 1 over 3x cube minus 1 over 4x in power 4, and with the substitutions from 1 to 3. So the following integral. Okay. So the following result. So 2. Okay, when I substitute here, so what I have, so 9 over 2 plus 9 minus 81 over 4 and minus 1 over 2 plus 1 over 3 minus 1 over 4. Okay, let we check these records. So actually, they are the same here. And let's believe that the final result is minus 44 over 3. So let we not waste time for arithmetics and more to advanced calculus. Any questions about this exercise?
Can you show full solution?
Yeah. Well, full solution maybe we cannot see on the screen, but which...
No, that's enough. Thank you.
Mm-hmm.
No questions.
From anybody else?
No questions.
Okay. So moving to the next exercise. So 1b. So we have the following integral. X x dy, and here L, of course. And L is the contour of the triangle formed by coordinate x's, and the line x over 2 plus y over 3 equals 1. So it is the equation of the straight line in the intercept plot, intercept form, and it is easy to plot it. And the direction is the positive counterclockwise. Let we look onto this plot. Yeah, by the way, let me write down also equations. So x equals 0, y equals 0, and x over 2 plus y over 3 equals 1. So how will we calculate this integral? We will split it to 3 parts. So for part AB, we will have the following. So for AB, y equals 0. So it means that dy equals 0 as well. So the integral along this segment equals 0. Now moving to BC. So for BC, let's express y. So y, we will move, so express y explicitly from this equation. So y will be equal 3 minus 3 over 2x. And then dy equals minus 3 over 2 dx. So the integral will be the following. Yeah, and by the way, limits of integration here, yeah, limits of integration. So x changes from 0 to 2, but we have to pay attention to the direction. So what does it mean here? That so if we go in direction BC, so the integral I BC will be the following. So we integrate from 2 to 0, and x multiplied by minus 3 over 2 dx. Okay, let me put it into brackets. So the following integral, and now let's transform it to a more convenient form. So 3 over 2 move in here, and we will turn over limits of integration. So the minus will go away, and we have just integral x dx. Oh, stop. From 0 to 2. So we have 3 over 4 x square with substitutions from 0 to 2. And it will be actually equal to 3. So for segment BC is done. And what about CA? So for CA, x equals 0. So the integral, so x dy along this straight line, along this segment, so not AB, but CA will be equal 0. And now we will calculate, so this, the result, the final solution will be sum of these integrals. So the final answer is 3. Any questions about this exercise?
Can you scroll down?
Yeah, sure.
No questions.
From anybody else? Okay, if no questions, let's move to the next task. So 1C. So we have the following integral. So y dx plus x dy, and L is a quarter of the circle, and given parametrically. So x equals r cosine of t, y equals r sine of t. And t has values from 0 to p over 2. So let's calculate differentials. So dx will be equal minus r sine of t dt, and dy equals r cosine of t dt. So we will substitute everything into the integral. So we have limits of integration, so we know them. So from 0 to p over 2. So y dx will be equal, so r sine of t by this expression, so minus r minus r square sine square over t and x dy, so plus r square cosine square of t dt. Let's simplify this expression. So let's move r square out of the integral. And actually what we can see here, it is the formula of the double, so of the cosine of the double argument. So it will be the following expression. So cosine of 2t dt. So we will receive under the integral. And now let's integrate. So r square over 2 a sine of 2t with the substitutions from 0 to p over 2. And of course it will be equal to 0. So it's done. Any questions about this exercise? Okay, if no questions, moving to the next exercise. Yeah, so usually parametrically given curves, it is much easier. Okay, moving to 1D. So the following integral along L to a minus y dx plus x dy, and L is the arc of the cycloid, so x equals a by t minus sine of t, y equals a by 1 minus cosine of t, and the first arc of the cycloid corresponds the values of t from 0 to 2t. And yeah, let's find differentials. So dx will be equal a by 1 minus cosine of t dt, and dy equals a sine of t dt. So let's substitute everything into the integral and calculate it. So what do we have here? 2a minus so 2a minus this expression multiplied by, so dx multiplied by this expression. And plus x dy. So a t minus sine of t multiplied by a sine of t. And now let's simplify this integral before we calculate it. So what can be simplified first of all? First of all, we will move a square out of brackets. So because everything is square, yeah, so we can simplify it. And now expanding brackets. So it is the next step. So 2 multiplied by 1 minus cosine of t, and it will, here will be the power of 2. So these brackets expanded. Yeah. No. It must be. So this bracket is odd. Okay. And plus t sine of t minus sine square of t. Now let's continue expanding brackets. And you will see that this integral will be simplified. So 2 minus 2 cosine of t minus 1 plus 2 cosine of t and minus cosine square of t. And now we will eliminate a lot of components here. So 2 cosine of t minus 2 cosine of t. So done with it. Then what about cosine minus cosine square minus sine of square? So it will be minus 1, and so 2 minus 1 minus 1. So what we will receive under the integral will be just t by sine of t. So this function. And this integral will be calculated by parts. So let's remember this formula. So u equals t, then du equals dt, dv equals sine of t dt, and v equals minus cosine of t. So we have minus t cosine of t with the substitutions from 0 to 2p. And plus integral, so of cosine of t. So the following integral. Okay, let's calculate here what we receive. So if I substitute 0, it will be 0, but if I substitute 2p, so cosine of 2p equals 1, so minus 2p, and plus sine of plus sine of t, with the substitutions from 0 to 2p, and it is actually equal to 0. So the final answer is minus 2p. Any questions about this exercise?
No questions.
Okay, if no questions, let's move to the next. So the next task is so 1e. Again, we will calculate the line integral, and now it is in 3D. So x dx plus y dy plus x plus y minus 1 dz. So we have the following integral, and it is the line segment from point 111 to point 234. So let's write down the equation of this straight line. So x minus 1 and over 1. Yeah, writing down the equation. So the line passing through 2 points. Y minus 1 over 2 equals Z minus 1 over 3. And now, yeah, it equals t, so we will write down the equation in a parametric form. By the way, let's write in line. So x equals t plus 1, y equals 2t plus 1, z equals 3t plus 1. Then dx will be equal dt, y equals 2 dt, and dy equals 2 dt, and dz equals 3 dt. What about limits of integration? Actually, we can see that if I substitute, so if I substitute 0, I have 1, 1, 1. If I substitute 1, so we can see from the equation. So if I substitute 1, I have 2, 3, 4. So t changes from 0 to 1. Yeah, and always if we have a curve or straight line in, so we need to integrate along a straight line or curve in three-dimensional space. We always have to parameterize this curve. So now substituting everything here. So t plus 1. Then y, so y dy, so plus 2 to t plus 1 plus, yeah, so plus 3 t plus 1 plus 2t plus 1 and minus 1 dt. Oh, now let's simplify this expression. So we'll expand the brackets. And here, let's first of all calculate this expression in these brackets. So 3t plus 1 so plus 9t plus 3. So 14t and plus stop. To here and to here plus 6. So we have to integrate this function. Yeah, and the function will, so the antiderivative will be the following. So t 7t square plus 6t with the substitutions from 0 to 1. And it will be equal 13. Any questions about this exercise?
No.
Okay, if no questions, moving to the next task, and it will be about Green's formula. So let's write down first of all the condition. So we have to integrate the function along the closed contour. So in this case, contour of a triangle. So 1 over y dx minus 1 over x dy. And L is a contour of triangle. And by the way, how to use Green's formula? So Green's formula, so it is the formula that connects the line integral of the second kind with the double integral. So if we have the closed contour, we can move, so we can transform to the through the double integral or by the region that L bounds. So bounded by L. So let's write down first of all functions. So P equals 1 from y, 1 over y, sorry. Q equals minus 1 over x. So now we need to differentiate. So dq by dx equals 1 over x squared. Then dp by by dy equals minus 1 over y squared, sorry. So we will rewrite the integral into the following form. So it will be the following integral. So we subtract, so from dq, so dq by dx minus dp by dy. So 1 over x squared plus 1 over y squared. Just a moment, I will plug in my laptop. Okay, so I'm back. And now, yeah, so we received such integral. So now let's define the limits of integration for this region. So we have the following triangle. So it is bounded by the following straight lines. So x equals 2, y equals 1, and y equals x. And now let's, so from this plot we will define limits of integration. So for x, well, x changes from 1 to 2. And what about y? Y changes from 1 to x. So let's write down this integral. So repeated integral. So 1 over 2, from 1 to 2 dx. And from 1 to x, this expression dy. Okay, calculating the inner integral. So what do we receive here? So y, y over x square minus 1 over y, and with the substitutions from 1 to x. So now let's do these substitutions. and everything will be simplified. So in the first case, so if I substitute x, what I will receive, so 1 over x minus 1 over x. And if I substitute 1, so 1 over x square minus 1. So what will I receive? Yeah, so it will be eliminated. So 1 minus x over 1 minus 1 over x cube. So let's integrate it. So from 1 to 2. So x plus 1 over x. So 2 plus 1 over 2 and minus 1, so the final result is 1 over 2. Any questions about this exercise?
No questions.
Okay, no questions, so let's move to the next exercise. Let's solve one more example. So when we integrate along the circle, the closed circle, so xy square dy minus x square dx. So p equals xy square. Oh, stop. Attentively. So here dx, so p equals minus x square. Yeah, and you don't confuse as well. And u equals xy square. So pay attention to dx and dy. So now dp by dx, or by by dy equals stop. Yeah, minus xy square. X square y. Yeah, forgot. And I see that something is not okay. So equals minus x square. Then dq by dx equals y square. So the integral will be the following. Yeah, okay, let's write down the integral, and then we will write down limits of integration. So what do we have? Y square plus x square dx dy. Okay, what about limits of integration? So first of all, we see that the region is around, so it is as it is bounded by this circle. So it is a good idea to move to polar coordinates. So as we integrate in the whole round, so yeah, by the way, let me remind you formulas. So x equals rho cosine of phi, and y equals rho sine of phi. So phi changes from 0 to 2p. And rho changes from 0 to r. Okay, so let's move. Yeah, and by the way, this expression will be equal rho square. So, writing down limits, so the new integral with new limits, so from 0 to 2p d phi, and from 0 to r rho square, and don't forget to multiply by rho. And this integral can be split to separate to two separate integrals. So product of two integrals. So r cube here. And now let's integrate. So this integral will be equal to p. And this integral 1/4 r in power of 4 with substitutions from 0 to r. So the final answer will be p/2 r in power of 4. Yeah, p/2 r in power of 4. Any questions about this exercise?
No questions.
Okay, if no questions, let's have a break for 5 minutes, and after that we will continue solving other interesting tasks. Let's continue. So we will solve the following exercise. So 3a. So we will check that the line integral sign is the total differential. And we will calculate this integral. So let's first of all write down the integral. To xy dx plus x square dy. So let's verify actually that this is so that we have a differential of so that we have total differential. So p equals 2xy and q equals x square. How to prove it? We need to check if derivatives of so dp by dy equals dq by dx. So dp by dy equals 2x, and dq by dx equals 2x. So we see that dp by dy equals dq by dx, and it means that we have a total differential under the integral sign. So let's so now let's let's restore the function under this integral, so with this differential. So we will calculate the following integral. So 2xy dx, and it will be equal to so x square y plus some function that depends on y. We don't know which of them, but we will find it. So let's now let's again differentiate by so let's differentiate by x. Oh no, not by x, but by y. So du by dy will be equal x square, so which is equal to this expression. Yeah, and plus also dc by dy. And we can see from this expression that this derivative is equal to 0. So c from y equals just c, so it is a constant. And then we will write that u from xy equals x square y plus c. So this expression. And how can we calculate the integral? So the following formula. So uxy with substitutions from the first point to the second. So 0, 0 to 2, 1. So x square y, so with substitutions to 1, so it will be equal 4, and actually if I substitute 0, 0, I will receive 0, and constant c will be eliminated. Any questions about this exercise?
No questions.
Okay, no questions. So B is analogical. And let's now let's find a function given by a total differential. So we will restore the function with it. So for A, actually this task is analogical, but more polynomials. So polynomial functions. So the differential is the following. So du equals 2x cosine of y minus y square sine of x dx plus 2y plus 2y cosine of x minus x square sine of y dy. Okay, it seems that everything is written down correctly. And now let's, first of all, let's verify that we have a total differential. So P equals 2x cosine of y minus y square sine of x, and Q equals this expression. So differentiating P and Q. So dp by dy equals minus 2x sine of y minus 2y sine of x. Then dq by dx equals minus 2y sine of x and minus 2x sine of y. And as we can see, these expressions are equal. So dp by dy equals dq by dx. So it is a total differential. Then we will use the following formula to find the function given by total differential. So u from x, y equals, so we will calculate the following integrals. So x, so the first integral from x0 to x, p from x and y index 0. So 0 dx, so we'll substitute y0 into expression for p. And what about so the second integral from y0 to y, q from xy. So without so it is a variable, not not a number. So plus c. So now let's calculate these integrals. So, by the way, let's choose the function x0, y0. We can choose any function that belongs to the domain. And in this case, so usually it is more convenient to take point 0, 0. Actually, this this expression really allows us to do it. So we will have the following integral. So dp, so p from x0, y0. So from x by y0. So this part's actually everything will be, oh no, this part will be eliminated. This part, And what remains? Only 2x dx. So we have 4x square with substitutions from 0 to 2x. So it will be equal to 4x square. So done with it. And what about this integral? So from 0 to y, from this function. So let's calculate the integral. So y square cosine of x plus x square cosine of y with the substitutions from 0 to 1. Well, from 0 to y. So we have, so this expression remains. And if I substitute 0, so this expression goes away, and plus x square. So that's it for these integrals, and now writing down the final answer. Stop. Minus, sorry. Minus here. Yeah. So now everything is correct. So what we will receive? So this expression and plus 3x square plus c. So we restored the function u by its total differential, and it has the following expression. Any questions about this exercise? Yeah, and by the way, let's check with answers in my records as well. Yeah, x square must be eliminated. Yeah, so something is not correct. Let's check once more. So what about this integral? So yeah, it equals 0, and so from x to 2x. Oh, stop. Yeah, 4x. So not 4x, but x. Yeah, my bad. So not multiplying, but dividing. So now everything is correct. So we have such expression, and if we differentiate, so if we find, for example, if we calculate the derivative by, so okay, let's just verify. So du by dx, yeah, so it is a good idea to verify your solutions. Minus y square cosine of x plus 2x cosine of y, and du by dy equals 2y cosine of x minus x square sine of y. And if we check with this differential, yeah, let's check it. Yeah, so the first derivative by x and the first partial derivative by y, so everything is correct. Any questions about this exercise?
No questions.
Okay, if no questions, let's move to the next exercise. So we will have to do some stuff with so we will solve some exercises related to application of the line integral of the second kind. So line integral of the second kind allows us to calculate area of the figure. Area of the figure that is bounded by the closed curve. So for the first, so in the first case, we have the ellipse that is given by the following equations. So in parametric form, so x equals a cosine of t and y equals b sine of t. Yeah, and by the way, how the area can be calculated. So the following integral. So x dy minus y dx. Yeah, and divided by 2 also, 1 over 2. So such integral allows us to calculate the area. So calculating dx. So dx equals minus a sine of t dt. Then dy equals b cosine of t dt. And what about values of t? So t has values from 0 to 2p. So now let's write down the integral. So from 0 to 2p. So x dy. So ab cosine square of t. And y dx, so minus ab sine square of t. But here is minus as well, so plus ab sine square of t dt. Now let's move ab out of brackets. So it will be simplified. Yeah, and actually this integral will be equal to 2p. And the answer is p ab. So actually this is the formula for finding area of the ellipse. And it seems that all calculations were correct. So any questions about this exercise?
No questions.
Okay, if no questions, let's move to 5b. We will solve one more exercise with the area. And here we will calculate the area of the arc of a cycloid. So x equals a t minus sine of t. Y equals a by 1 minus cosine of t. Then dx equals a 1 minus cosine of t dt, and dy equals a sine of t dt. What next? What about limits of integration? So t from 0 to 2p. So the first arc of cycloid. So now, so calculating the integral. First of all, writing down the expression for this integral. So what do we have? X dy. So this expression by this, and minus y dx. So x a square by this expression in power of 2 as well. So now let's simplify this integral before calculating. So first of all, moving a square out of brackets. Lost dt. So now let's expand the brackets. So t sine of t minus sine square of t minus 1 minus 2 cosine of t and plus 2 cosine of t and minus 1 plus 2 cosine of t and minus sine square of t. And what will be simplified? Cosine. Sorry, cosine square of t. Yeah. So this expression is done, and this done as well. So minus 2. So which expression we received? So it can be easily calculated. Yeah, let's calculate separately the following integral. So I1, so we will calculate t sine of t, so we will integrate it by parts. So u equals t, then du equals dt, dv equals sine of t, dt, and v equals minus cosine of t. So minus t cosine of t with the substitutions from 0 to 2p and plus integral of cosine. So what do we have here? Here we have minus 2p for this expression, and plus sine of t with substitutions from 0 to 1 to p or to p. So it is equals minus 2p. And let's calculate separately this integral. So I2. So we will integrate so 2 cosine of t minus 2 dt from 0 to 2p. So it will be 2 sine of t plus 2t with substitutions from 0 to 2p. So it will be equal to 0. And what do we have here? 4p. So what do we receive here? So a square over 2 multiplied by 4p minus 2p. So it will be a square p. So calculated. Any questions about this exercise?
No.
And let's just verify the area of a cycloid. Mm. 3pa square. And y? 3pa cube. 3pa square, but y. So it seems that we missed something. So a square, okay, here. And let me check other resources. Three. Why 3? Okay, now let me double check it. So a moved away. So t sine of t minus sine square of t. Then minus 1 plus 2 cosine of t minus cosine square of t. Minus. Minus and it is even more interesting in this case, but why minus? Yeah, minus, so we have minus 4p here. And how to deal with these minuses? Yeah, so it cannot be negative, actually. That's not okay. So again, missed something. Minus y dx. Y dx. So maybe anybody else noticed that we somewhere lost the sign. So x dy is this expression. So yeah, is correct. Y dx as well. So what is going on? So actually this integral is taken correctly. And this as well. Okay, let me check this. Let me check it later. But yeah, so we just confused the sign everywhere. So the area must be 3pa square. And now we need to solve more exercises with the usage of with application of the line integral of the second kind. So maybe now you have some questions or you noticed something.
No questions.
Okay, so now we need to calculate the work of the force. As you know from physics, that not closed, not always. So that it can be calculated by the following integral. So scalar product of force and dr. And the force is given by the following formula. So y square I plus x square j. So actually, yeah. What about the curve? So it is parabola that we already know, y equals x square, and we need to calculate from the work from this point to this that force does. So for this case, x reaches values from 0 to 1. Yeah. And y actually has explicit expression x square. So the integral will be the following. So L, and so y square dx plus x square dy. And dy will be equal to x dx. So we will transform it to the definite integral from 0 to 1 x in power of 4 plus 2x cube dx. So now let's integrate. And what we will receive? So 1 over 4 x in power of 5 plus 1 over 2 x in power of 4 with the substitutions from 0 to 1. So it will be 1 over 5 plus 1 over 2. And the final answer will be 7 over 10. Any questions about this exercise?
No.
Okay, if no questions, moving to the next exercise, we will have another case. So now we solve the task in three-dimensional space. So the work is the following: zi plus xj plus yk. So it is the force. And it will be, let's write down formulas for L. So x equals t, y equals t square, and z equals t cube. And the integral will be the following. So integral by L, so z dx plus x dy and plus y dz. So now let's find differentials. So dx equals dt. then dy equals 2t dt, and dz equals 3t square dt. And what about value of parameter t? So we can see that so 0.000 and 0.111. So it means that yeah, and by looking at these formulas, we write down that t is so we figure out that t is limited by values, so from 0 to 1. So bounded by these values. So now we will write down the definite integral. So from 0 to 1, then z dx, so t cube, then x dy, 2 plus 2t square, and what about y dz? So plus 3t in power of 4 and dt. Let's double check a little bit. So z dx, yeah, correct. Then x dy, correct, and y dz, correct as well. So now we will integrate. So we will have the following expression. So 1 over 4 t in power of 4 plus 3 over 2 t in power of 3. Stop. Yeah, correct everything. Plus 3 over 5. Plus 3 over 5 t in power of 5. And we with substitutions from 0 to 1. So we have the following expression. So I will just erase t. And let's find the common denominator. So the common denominator will be actually 60. If we look here, yeah. So 15 over 60 plus, stop, 2 over 3.
20, probably.
Yeah, from 2, yeah, 2 over 3, so now everything is correct. Plus 40 over 60, and plus 36 over 60. And if I add, I will receive 81 over 60, and we can reduce it by 3. It will be equal to 27 over 20. So it's done. Any questions about this exercise, about the whole lesson, about previous lessons?
No questions.
Okay, so now we are finishing the lesson. Stay safe. Thank you for your attention. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.